So continuing on, in this section we're going to look at the atomic spectrum of hydrogen. We call this a line-emission spectrum, and you'll see why once you see sort of a picture of what it is. Scientists discovered that light is emitted by excited hydrogen atoms when the bond between the two hydrogen atoms is broken. So you know hydrogen is diatomic H2, right? So if you break that bond, you break the hydrogens apart, they'll give off light. And the reason is because of what happens with the electrons. So some terminology: ground state. The ground state is the lowest energy state for an atom when its potential energy is at its lowest point. Excited state for an atom is when the atom has higher potential energy than it does at the ground state. So you've added energy to the atom, and that atom's potential energy then goes up because it now has more energy, internal energy, than it did. That's called the excited state. Okay? So a line emission spectrum is a series of specific wavelengths that are created when the visible portion of light that is produced from excited atoms is shown through a prism. Prism is just a glass or plastic device, medium, that slows down certain wavelengths of light and therefore causes them to bend a little bit. And so we think of a prism as separating out wavelengths, but it really is slowing certain ones down so that they take longer to get through the medium. Okay, so scientists using sort of classical theory about energy and particles, when they did this, they expected that atoms would always be excited whenever they absorbed energy. Okay, the continuous spectrum is when you see a continuous range of frequencies of electromagnetic radiation. It contains all of the wavelengths of visible light. It's a rainbow. Okay, a true rainbow. Visible light, if it contains all the wavelengths and you pass it through a prism, you will see all of the different colors. Okay, so here we have at the top, we have a white light source, and white light is all of the visible light. We pass it through a slit to sort of focus it, pass it through a prism, and the prism causes certain wavelengths to go through more slowly and others to go through more quickly, and then the angle of the prism allows for some bending. And so what happens is the prism splits the white light into its wavelengths, but because it contains every wavelength, not just red, orange, yellow, green, blue, indigo, and violet, but all of the colors in between that we don't actually have, easy names for. It's a smooth rainbow across. However, if you take hydrogen in a tube and you add high voltage through it, which excites the atoms, they produce some light as well. And if we focus that light through the slit and through a prism, instead of seeing a very smooth looking rainbow, what we actually see is a lot of black space. No light goes there. But there are 4 specific lines, which are always the same 4 lines, that are emitted. These 4 lines at 410 nanometers, sort of purple, 434 nanometers, sort of like a dark bluish purple, 486, which is kind of a light blue, and 656, which is sort of an orange bordering into towards red. It's always those 4 lines that are emitted by excited hydrogen, hence the name line emission spectrum. Okay, the black spaces in this spectrum means that there are no wavelengths in those areas emitted by hydrogen. Okay, so these 4 lines, we always see them, and the question then came up with, well, why do they always give off those specific frequencies? It took the development of current quantum theory to be able to explain this. So what we understand about electrons is that when you take an electron and you give it energy, it jumps. It moves to a higher energy state. And that means it moves further away from the nucleus. So one of the most important things to get out of this is that the distance from the nucleus is proportional to the energy of the electron. Okay? It doesn't like to be there, so it comes back to the nucleus and it gives off a photon. The energy of that photon is equal to the difference in energy from its initial and final state. So the amount of energy that the photon has, which we can easily calculate if we know its wavelength, is equal to the amount of energy that that electron absorbed in the first place to jump. Okay? Now, for hydrogen, only certain wavelengths, certain colors were emitted. Right? That means that the hydrogen's electron is only able to jump to certain distances. That's what that means. So Bohr was the first to take this information and make something out of it. Okay? Niels Bohr, Danish physicist, 1913 was working with hydrogen and came up with his first quantum model. It's the one we all know. Okay? He used the model to help explain why we always saw those same four colors for hydrogen, those same four lines. So Bohr said that electron circles the nucleus like planets around the sun, and it can only exist in certain orbits. And the orbit that it exists in is dependent on how much energy that electron has. Okay? So he couldn't use sort of the classic ideas of physics. We had to understand this concept of quanta of energy being absorbed by the atom, and that energy being a finite amount, an amount that we could actually calculate. So he created an equation that he would use to calculate how much distance the electron had from the nucleus. In other words, where the energy levels for this electron were, where the orbits were. It looks like this. Okay, E is equal to negative 2.178 times 10 to the minus 18th joules. That's a constant. And then we have z squared over n squared. N is an integer, and z is the atomic number of the atom. Okay, the fact that it's negative means that as you move closer to the nucleus, the energy is negative, which means it's coming out. It's exothermic, right? So as an electron moves back closer to the nucleus, it gives off energy. It's exothermic. If you want to move the electron away from the nucleus, you have to put in energy. E is positive, endothermic. So Bohr came up with this idea that there were these energy orbit levels, right, at different distances from the nucleus. And you can have an electron can gain energy, and it moves to a higher energy level when it gains energy. But when it comes back down to a lower energy, it loses or releases that energy. And it releases that energy in the form of a photon. So what Bohr was saying, is this hydrogen's electron is moving to one of four different levels. And if it moves very far away in the blue region, perhaps, when it comes back, it gives off that particular wavelength. And if it doesn't move quite as far, if it moves only a small distance, then it's only going to give a small amount of energy back, and that would correspond to a longer wavelength, the orange line. That's Bohr's idea. Okay, so as an electron gains energy, it moves, jumps to a higher energy, and as it comes back to ground state, it releases a photon that has the same energy as the amount it gained, and since energy and wavelength are related, it gives off a particular wavelength. That's the colors that we see. Okay. We can take his equation, and if we want to figure out, how much energy is gained or lost when we move from one energy level to another, we can combine two of these equations. So this equation twice, it looks sort of like this. That's kind of big and scary looking the way it is. But all we've done is we've taken the equation for the final location, the final energy level. That's what n is the integer representing the energy level, 1, 2, 3, 4, 5. And we've subtracted from that the energy at the initial n sub I. Now, that's how we do delta anything, final minus initial. So let's clean this up a little bit. Okay, so we sort of factor out common terms, etc. We get delta E is equal to negative 2.178 times 10 to the minus 18th joules. That's the constant. And then we have this expression, 1 over n final squared minus 1 over n initial squared. And if we use that, let's say that we want to figure out where was the electron when it released this amount of energy. We would know the amount of energy, delta E, and we would know where we started, perhaps, Ni, and we could find Nf, or any variation, any one of these variables. There's only three variables in this equation, delta E, n sub f, and n sub I. Since we can find the energy, we can also use the relationship between wavelength and energy to figure out what the wavelength of that photon would be. In other words, what color it would be. Or we can go backwards. We could start with the color, find delta E, and then go back and calculate the change in energy levels that would have had to have happened to give you that. Okay. Now, what about when E is equal to 0? If E is equal to 0, meaning there's no energy of the electron, what we're assuming is that the electron's completely gone. Okay, it's left completely. So because as you get closer to the nucleus, the energy gets more and more negative, as you get further and further away from the nucleus, it becomes more and more positive, and eventually you can get to 0. Okay, so at a distance of infinity away from, in other words, the electron is gone, we say E is 0 for the electron. It's gone, it's away from the atom. Okay. So there are some problems with Bohr's model. The first is it doesn't work for other atoms. It only works for hydrogen. That's kind of a problem if you're trying to create a model. And it doesn't explain chemical behavior of atoms. That wasn't sort of handled by this model. So here's an example we'll take you through real quick. We're going to calculate the energy required to move the hydrogen electron from n equals 1 to n equals 2. And then we're going to find the wavelength of the radiation that had to be absorbed. You're going to want to pause the video and follow along with the math to make sure you understand it. So here's our equation. Delta E is negative 2.178 times 10 to the minus 18th joules times 1 over n final squared minus 1 over n initial squared. Our final, if we're moving the electron from 1 to 2, our final is 2 and our initial is 1. Okay, so let's plug in some values here. So we have that 1 over 2 squared minus 1 over 1 squared. And when we solve for delta E, we get 1.633 times 10 to the minus 18th joules. That's how much energy is required to move the hydrogen electron from n equals 1 to n equals 2. All right, so what's the wavelength of that? Well, let's solve for the wavelength. Wavelength is hc over delta E. So we can put in h, Planck's constant, c is the speed of light, and delta E is the amount of energy we just calculated, and we come out with 121.6 nanometers. You should know or remember that when you calculate lambda using any of these formulas, it's always going to come out in meters because the speed of light is in meters per second. So if you want it in nanometers, you have to change it, convert it into nanometers. All right, your turn. Try this one. We want to remove the electron completely from the hydrogen atom. Okay, go back and look at the previous 2 slides to figure out how to do this, but give it a try, and we'll take a look at it in class.